All right, so in part one, hold on a second. Okay, we're back. In part one of this recitation, we looked at derivatives and integrals. So after looking at the derivatives and integrals in the last part of this, I want to spend some time looking at arc length and curvature, which are some of the big things some of the big geometric questions we can start asking about curves in space. So let's do that. So still got the same whiteboard as before. So here's a question to start us off with. Let's suppose we want to find, so now this is about arc length. So if you've got a curve and it's parameterized, and that's just a fancy way to say given by, it's given by this function r of t, and r of t is just these three different functions, f of t, g of t, and h of t. It's parameterized by this function for t between a and b. Then the length of c is given by the formula L equals the integral from a to b of the magnitude of r prime of t dt. Unpacking this for a little bit, this should actually make a surprising amount of sense, and here's why. R prime of t, you remember, that's speed, right? Now r prime of t itself would be velocity, but we're taking the magnitude of it, and the magnitude of velocity, so velocity ignoring direction, that's just speed, right? So it's speed times a very small unit of time. So speed times time, we think about that, that's distance. Right? Speed times time is distance. So all of this is doing is adding up all the little bits of small distance. It's, in other words, integrating. Integral is. It's a whole bunch of adding up teeny tiny bits. So that's what this length of c is. That's the arc length formula. Let's see what we can do with that. Let's take, for example, the curve c parameterized by r of t. R of t is going to be given by e to the t sine ti plus e to the t cosine tj plus root 2 e to the t k for t between 0 and 1, say. It doesn't have to be between 0 and 1, that's just an example. And the length, the arc length, is the integral from 0 to 1 of the magnitude of r prime of t dt. Now what do we need? Well, the first thing we're going to need to do is to find r prime, right? So I'm actually going to, in keeping with my style, I'm going to do this in blue to show that we're answering the question now. R prime of t, we're going to need to know this. R prime of t, we go through this. Well, that's going to be e to the t sine t plus e to the t cosine t, that's product rule, I, plus, same story, e to the t cosine t minus e to the t sine t, again, product rule, j, plus root 2 e to the t. Okay, now we're going to take its magnitude. Magnitude of r prime of t, and you really do have to take the magnitude. That is not negotiable. If you don't take the magnitude, then you're just anti-differentiating r prime, which is just r, which is silly. We're not doing that. So what we are going to do is anti-differentiate r prime. How do we? So what's that going to look like? Well, what are we doing in that case? What we're going to do is find the square root, right? Great big square root of the square of et sine t plus et cosine t. It's going to be e to the 2t sine squared t plus 2e to the 2t, because it's still e to the 2t, so e to the t times e to the t, 2e to the 2t sine t cosine t plus e to the 2t cosine squared t. That's the first square term. It's still got a ways to go with this big honkin' square root. Same story, plus e to the 2t cosine squared t minus 2e to the 2t sine t cosine t. And that's good news because that's going to cancel now. Plus e to the 2t sine squared t plus 2e to the 2t. That's coming from the last term. Continuing on. E to the 2t sine squared t, e to the 2t cosine squared t. That first term is going to become just to recap, e to the 2t times sine squared t plus cosine squared t. That's just 1. Happens again. E to the 2t times cosine squared t plus sine squared t plus 2e to the 2t. The whole thing, having done all this, is going to become the square root of 4e to the 2t, or in other words, 2e to the t. I mean, we should just undo that. 2e to the t. So the upshot of this is that the length is the integral from 0 to 1 of 2e to the t dt. And that's easy enough to calculate. That's just 2e to the t evaluated from 0 to 1. In other words, that's 2 times e minus 1. That's the length. That's the length of the, I don't know what exactly this curve looks like, but it's going to be some kind of weird curve. And its length, we now know. Length of that curve is 2 times e minus 1. So far, so good. We also, though, have something called the arc length function. Now, what is that? The arc length function we think of this as an odometer of these objects. So the arc length function is written as s of t. Actually, I have to be a little more specific before I write this out. The arc length function from some point P with position vector R naught. What does that mean? It means that, i.e., we have that R naught, R0 is ABC, and the point P is just the point ABC. So the arc length function is what? It's s of t. S usually, I don't know where this comes from, but s is usually used to denote distance for this purpose. S is from 0 to t of magnitude r prime u, again, du. Again, we have to use u and not t because we already have t in the limit of our integration. What is this? This tells us the position, or rather, this tells us the length traveled, the distance traveled, this is the distance traveled along the curve after time t from the initial point. So let's return to our example from before. Our example from before was R of t. R of t is equal to the, what was it? R of t was e to the t sine ti plus e to the t cosine tj plus root 2 e to the t k. So the arc length function from the point p01 root 2, well, p01 root 2, that's satisfied at t equals 0. So since r of 0 is 0, 1, root 2, we get that s of t is the integral from 0 to t of magnitude r prime u du. Now, we know what r prime u is, by the way. We know, we had already calculated that that's the integral from 0 to t of 2e to the u du. 2e to the u, so what's that going to be? That is, so that's going to come out to be, let's see. So what's that going to come out to be? That, as we anti-differentiate that, is just 2e to the u from 0 to t, or in other words, 2 times e to the t minus 1. So that's the arc length function. Now here's another question. Here's another question that we can ask. The other question we can ask is at what point? Actually, let me phrase this a different way. So, where are you? So if you're traveling along the curve, where are you along curve after traveling for 4 units of distance? In other words, if your odometer tells you you've been traveling for 4 units, for 4 miles, where are you at that point? To do this, to answer this question, we're going to use what's called the arc length parameterization. Which means we're going to rewrite R of t, your position, in other words, in terms of s, your distance traveled. Well, we know in this case that s is equal to 2 times e to the t minus 1, or in other words, 1/2 s minus 1 is, yeah, that's right. 1/2 s minus 1 is equal to e to the t, or in other words, t is equal to ln of 1/2 s minus 1. So r of t, in other words, r of ln 1/2 s minus 1, this is the arc length parameterization. What's that going to come out to? That's going to come out to 1/2 s minus 1 times sine of ln 1/2. I gave this too many. 1 second. Let me re-express that. 1/2 s minus 1. Sine of ln 1/2 s minus 1. I plus 1/2 s minus 1 cosine ln of 1/2 s minus 1 plus root 2 times 1/2 s minus 1, because it's e to all of these things, so it's e to the ln of all that stuff. Oh, and I forgot, there's a j here and a k here. All of which is to say that what we have at this point, so where are we after 4 units of distance? Well, after 4 units of distance, set s equal to 4. Your position in that case becomes r equals 1/2, so 4, so 2 minus 1, in other words, that's sine of ln of 4 minus, of 2 minus 1. That's 0, in other words, I, plus cosine of ln of, again, it's 1, plus root 2 times 1. Oh, again, I forgot the j and the k. Oopsie. Which, in other words, just comes out to cosine of 0 is 1, so it's just j plus root 2 k. Or in other words, you're at the point 0, 1, root 2. Now, root 2, sorry. Wait a second. Okay. Actually, after looking at this for a little bit, I realized that I made a very silly mistake. So ignore all of this stuff. This is all completely wrong. Let me try this again. Hopefully, in a more reasonable and not ridiculous way. So let me fix all this stuff that I whoopsie. Oops, oops, oops. Big oops. Big oops. Okay. Let's try it again. S equals 2 times e to the t minus 1. We know that. So that means in this case that that 1/2 s plus 1, it was a plus 1, or should have been minus 1. That's going to be e to the t. So now we know that t is ln of 1/2 s plus 1. Now we can say what we wanted to, so that the arc length parameterization is r of s in this case is still, we have e to the t, so that's going to be 1/2 s plus 1 sine ln 1/2 s plus 1 I plus 1/2 s plus 1 cosine ln 1/2 s plus 1 j plus root 2 times 1/2 s plus 1. Okay. And r of 4, plugging in r, because it's distance 4 that we're interested in, so r of 4 comes out to 3 sine of ln 3 I plus 3 cosine of ln 3 plus 3 root 2. J and K. I always forget the J and the K. I don't know. And why the J and the K specifically? It's always those two. So the final position, in other words, is 3 sine of ln 3, 3 cosine ln 3, 3 root 2. That's your final position after having traveled for 4 bits. That's what the arc length parameterization really tells us. That's why it's really useful. Okay. And arc length parameterization seems to often be sort of a point of confusion for a lot of students. So, and I'm not always sure. It's mostly just this odometer. Like I said, it's a new way of showing how to get this curve. That's really all that it comes down to. So I'm going to stop here. Thank you, everyone, for your for tuning in. If you're watching this later on, and I will talk to you guys on Friday when we do some of the challenge problems that we talked about for Chapter 13.